wanted to start by saying that I very much still feel like a student learning the field of robotics and having a lot of fun working in robotics with my super amazing students like Juan. So thank you so much. I thought I would give a relatively playful title, but just spend this time sharing some of my thoughts on AI vision and robotics. So the title is Octopus, Kittens, and Babies from Seeing to Doing. And the outline is I'll try to fit in two parts in this talk. The first part is probably where most of you know my work, is a brief history of computer vision and connecting why I'm so excited to connecting vision to robotics, why seeing is for doing. And the second part is focusing on a couple of line of recent work in my lab and with my collaborators on a more vision-driven robotics and how we can enable vision and hands or grippers to interact with the world. So let's see how far we can get through this ambitious agenda. Of course, I'm preaching to the choir. This, I understand this is a robotics heavy community, but many of you are vision and AI experts. And I've been in the field of vision for more than 20 years, and it still wakes me up every day with so much excitement. Vision is just fundamentally a cornerstone of intelligence for animals since the dawn of evolution, as well as for very advanced animals like humans, where vision as a sensory system occupies half of the brain, or in a more precise way, half of the brain, cortical brain, is involved in visual processing, which is a huge real estate to devote to in a highly complex neural system. And the reason being that vision is very complex and it's so essential in every part of our intelligence. So as Quan said, a lot of colleagues from other fields of AI and machine learning, and also the public, get to know computer vision's progress recently or in the past decade through tasks like IMAGENET, where we are, as a field, collectively able to use neural network architecture, especially convolutional neural network architecture, to perform actually pretty impressive tasks like 1,000-way object classification. And everybody knows that the year 2012 was the beginning of the watershed moment for deep learning because of the Jeff Hinton and students' paper on ImageNet challenge. And that brought us what many people call the deep learning revolution, which is truly a incredible convergence. As a result of an incredible convergence of three forces: the computing power, the algorithms, especially neural network, and data. And then the world sees an explosion in AI growth by any measure, whether we're talking about conference attendance, startups, markets, and all this. But I want to go back a little bit to actually where we came from, because we hear all this, but where did all this? Why did we come to the year 2012? And what does this mean to our future research direction? And how does that connect to my personal excitement for vision and robotics? So there is a part of the story that is quite well known to everybody, is the neuroscience-inspired neural network algorithm. And that laid the foundation of neural network algorithm. And for those of you who are new to this, Hugo and Wiesel in the late 1950s, two very smart postdocs at Harvard, were experimenting with recording cat visual cortex, and they found that this is a in the early stage of cat visual processing, the neurons respond to simple oriented edges, like what they call oriented bars. And furthermore, Hugo and Wiesel found that mammalian, using cats, visual system is organized in a hierarchical way, that information is processed from lower level edge-like information all the way to the more complex object-like information. And that key insight of how visual neural, from neuroscience, how visual pathway is organized in a hierarchical way, first of all, won them a Nobel Medicine Prize in 1981, I believe, but more importantly, laid the foundation for a family of algorithm called neural network. In fact, you know, cross-disciplinary science is always where excitement is, even as concurrent as the cat environment was, cat experiment was going on. Computational neuroscientists and computer scientists are already experimenting with that hierarchical model back in the late 1950s. And of course, the most major breakthrough in terms of a learning rule came in the 1980s by Ramanhart, Hinton, and Williams on backpropagation. So I think it's fair to say that neuroscience was a major source of inspiration for neural network algorithm. But there is also, it begs the question, what happened between 1986 to 2012? It's almost 30 years. How come the field collectively in vision and AI and machine learning took that long to get to one of the holy grail problems of vision? Is it really just because there wasn't enough data, or we're waiting for the GPUs to be invented? So, sorry, the second part of this history, which is in parallel to the first part of the history, is actually less known to many of the students in the field, which is not just the history of the algorithm, but the history of searching for holy grail problems in science, or sometimes I call the search for North Star problems, is that we have this set of incredible tools, but what do we use it for? And this goes back to what vision, the history of vision as a field. Again, computer vision started in the same time as the early AI work. Larry Roberts is credited allegedly for writing the first PhD thesis in computer vision in 1963 on basically shape understanding using image analysis process. And of course, you can see this is very synthetic world. I wouldn't even call this block world to the extent of what block world could be. It's just really a couple of examples and looking at how edges produce 3D shape. Interesting, Larry Roberts left the field of computer vision and contributed greatly in the advances of the internet later in his career. But the field of computer vision began in the 60s and started this long, winding journey of searching for its North Star. Of course, I'm not saying there is only one North Star, but it's also true the collective community of computer vision spent quite a bit of time trying to understand what are the most foundational problems to work on. And of course, with the inspiration of neuroscience, the first try was edges. People believe understanding edges is really important, and a lot of papers and conferences were devoted to edges and segmentation. It continued to be an important problem, but that was just one milestone or one part of the search. Another important part of the search was 3D vision, especially coming from computational geometry and those, animal vision, especially stereo animal vision, were able to triangulate the world and understanding depth. So how do we do that in computer vision? So there is a lot of work in 3D vision. I would say decades of dominating topic is 3D vision in computer vision, which brought us important applications like Google Street View and so on. And then late in the 90s, some early pioneers start to turn their attention to object recognition, but mostly on single object recognition, like this seminal work on SIFT. Some of you old enough like me might remember that SIFT was as hot as deep learning back in the 90s and early 21st century. But that was just searching for the particular teddy bear or telephone in a picture. So if you look at the distribution of CVPR topics at the turn of the century, it was focusing on low-level vision and so on. And there wasn't much of a holy grail or North Star yet. In the meantime, major advances is happening in the sister field that is going to have a profound impact in computer vision and AI. And it's a different branch of neuroscience. It's not neurophysiology like Hubel and Wiesel, but cognitive neuroscience. Just a couple of seminal work to show you. Starting in the 70s, psychologists are showing us that object detection and recognition is a foundational capability of human vision. This is a seminal work from MIT's Molly Potter looking at RSVP technique to show you even with 10 hertz speed, which is 100 milliseconds per frame, humans have no problem of detecting a novel object, which I would call a person in the woods, and you will have an understanding immediately of where the person is, what the gesture is, even though you've never seen a picture or sequence of frame like this. And then cognitive neuroscientist Simon Thorpe and his colleagues did this seminal work in Nature in 1996, showing that the speed of complex object categorization task in human brain can be as fast as 150 milliseconds. I know that for those of you interested, more familiar with transistors, this is not an impressive speed. But those of you who work with animal brains, this is a very, very phenomenal speed. It also means it doesn't allow too much feedback time for the neural circuitry. And it also shows how innate this capability of complex object categorization is. And finally, one last work that I think is foundational and very seminal and have a profound impact in the field of computer vision is Nancy Kevensher and her colleagues at MIT finding that there are devoted brain areas showing that humans can do object categorization, especially things like faces, places, eventually body parts, and so on. So all this incredible work in cognitive neuroscience was actually a quiet revolution that impacted the field of computer vision. It's a revolution that pointed a North Star for computer vision, which is that the problem of object recognition at the category level is a really important problem to solve. And the field quickly rallied around this problem in the early years of 21st century. Many middle-sized data sets start to appear, especially the Pascal VOC data set that pioneered the way for the field to work on the problem of object recognition. And personally, I got into this, of course, through my work with Pietro Perona at Caltech in my PhD time, but I also got into this through another giant in cognitive science, not in the vision field, but in the language field, by George Miller at Princeton. And I was happened to be a junior faculty there and learned about his work in organizing the world's concepts through WordNet and pointing out the scale of concepts and categories in human brain or human mind. And that scale is just daunting. And that inspired us to work on this ImageNet data set because we saw this is a fundamental North Star for the problem of computer vision. And by putting together ImageNet and ImageNet Challenge, we not only can create a North Star, we can also create a path for the field of computer vision to reach that North Star. And the rest is history. Neural network dominated the few years of ImageNet Challenge result. And these are some of the example winning early winning architecture of ImageNet classification and detection tasks from the 7-layer AlexNet, and then GoogleNet, VGGNet, all the way to 151-layer ResNet, and now there's way more, countless number of architecture in working on these problems of object recognition and detection and so on. And personally, this success of the field of computer vision on image classification also got myself interested in inching toward a dream I had since PhD time, which is storytelling of images. So it's not just enough to give one label to a picture like this, is a horse carriage or person, but to tell the story. So concurrently, in the year around 2015 and so on, not only my own lab, but many labs around the world started working on this problem of image captioning, of telling the story of a picture like a man riding a horse-drawn carriage down the street, to longer captions of trying to describe different parts of the image, which we call dense captioning, all the way to paragraph captioning. Frankly, I was very surprised myself, even though I work in this, how fast the field was making progress, because the capability of storytelling of pictures was such a far-reaching goal for so many years. But in a few years after ImageNet challenge, quickly the field made a lot of progress. So we became very unsatisfied with just trying to tell the overall story, most likely by matching some language patterns. So my students and I started working even deeper into image understanding and focusing on relationship understanding. Relationship understanding, I don't have time to elaborate on this, but it's also something that cognitive scientists have been looking at for many years and thinks this is a really important capability of human perception, human cognition, and especially for social reasons. So we put together a new representation, which we call scene graphs, that connects entities, mostly the objects and subjects of a scene, with their relationships or predicates in the language of NLP, and try to represent a very visually rich picture or frame with this kind of scene graph depicting the relationships and the stories in the scene. I'm not going to elaborate on this, but a lot of work have followed that line of work, including our own, but also in other labs, using scene graph to compose scene representation or visual representation. And we used this very powerful tool on image retrieval, relationship understanding, image to scene graph automation, sentence to scene graph, as well as a GAN technique from scene graph to images. So there's a lot of fun work we have done this. But I'm not going to continue to keep talking about this line of work, partially because we start to recognize we're in a Plato world, which I call the allegory, which Plato called the allegory of the cave. What is this Plato problem? Well, the Plato problem is static vision. Plato described the scenario of what vision is, which I actually disagree with Plato now, but the way he described it is vision is, you imagine prisoners being tied down on chairs, and they're forced to watch a real world play, which was happening behind their head, so that then they're not allowed to turn their head. So all they could see is a 2D projection on the wall of what's going on in the actual 3D play back in their behind them, and they are not even allowed to move around to even experience this fully. So they're these static observers of a world outside of them, and of course a impoverished 2D world outside of them. So that's what Plato described as the allegory of the cave problem. And I feel like many of the vision problem we've worked on is sort of in the eyes or in the shoes of these prisoners in the allegory of the cave, but real vision is much more active. In fact, real vision is all about being active. So this moved us from thinking about vision in a static way to an active way. And this is the claim I'm gonna make, that much of seeing is for doing. So why do I make this claim? Well, first of all, evolution seemed to believe that or have proven that. There was a period of Cambrian explosion back in 530 million years ago. In a very short period of time, lots of species, animal species, evolved within that explosive time, which we zoologists call the Big Bang of evolution. And it's a puzzle why this happened. A long story short, modern zoologists found through fossil studies that it was the onset of sensors, especially vision, but also antennas and tentacles. And that onset of these perceptual sensors was critical to get the animals moving. And once the animals are moving, they need to evolve, because if they don't, they become somebody's dinner. So it seems vision was driving evolution or speciation, and it was also driving the sophistication of the intelligence of animals. So that's the evolutionary angle. There's also the baby angle. I did promise baby in my title. And many of you, I know, that are fans of Alison Gopnik's work, and so am I. And she represents a pioneering group of developmental psychologists, and also she's a philosopher, who are really telling us that early development is very much on the move. It's very much exploratory. It's very much the combination of perception and action and manipulation and navigation coming together to give the brain the needed dosage of stimulation. And this has a profound impact in my thinking, as well as many of the people in the field of AI these days. Last but not least, I also want to give another example to try to convince you that vision, seeing, and doing are critical. And this goes to the kittens. This is another thing I promised during my title. It's the Held and Hein kittens. In 1960s, in the seminal experiment, which I'm not so sure can pass IRB these days, they took 2 newborn kittens and they put them on a yoke and allow them to move in an environment. But sadly, sadly for both, they're somewhat confined, but especially sad for the pea kitten. If you can see my cursor, is very much confined to a box that it's not allowed to move at all, apart from some minimal movement. And then there is this A kitten, as sad as it's on the yoke, it's allowed to drive the yoke. And it's walking, it's turning its head, and so on. And after a few weeks, they released the kitten, and they realized that developmentally, the pea kitten was severely lacking in many ways, especially the perception system, but also just severely lacking, whereas the A kitten, the active kitten, developed pretty good systems, both motor-wise as well as perception-wise. So this is a profound experiment that links perception to action, or seeing to doing. There is a bi-directional relationship between perception and doing, and how we interact with the world. So I want to just say that at this point, we strongly believe intelligence emerges from active perception and interaction with the real world. And with this thesis, we want to see how far we can push AI system. And to do that, I just want to highlight a few ingredients of this statement of active and interactive intelligence. One is it is embodied and active. It's simultaneously exploratory and exploitative. Did I have a typo here? It's also multimodal, so sensory systems includes vision, olfactory, audio, tactile, and so on. It's very much multitask and generalizable, and it's social and interactive. And we're nowhere near covering all these important characteristics of intelligent system, but these are the characteristics that I find very exciting and think the direction of AI and robotics research is. So with that, I'm just going to briefly show you 3 lines of work that our own lab is doing in translating that philosophy of seeing is for doing and interaction with the real world into a couple of lines of work in robotics or RL. The first one is trying to just be inspired by baby actions. This is less of robotics, more RL. Collaboration with Dan Emmons and Nick Haber and student Damien. And the idea is that curiosity drives babies. They explore the environment so that they can learn. So translating that into an AI system, our work tries to learn a self model that tells the baby or the agent how to explore the world, and then a world model that constantly gets updated by the exploration of the self model and the interrogation of the real world. I want to just make sure, given time, I'm not going to be able to call out some of the inspirational work and contemporary work. I leave it in the citation section. And here's just the result to show that if you look at the time axis on the x-axis about how the system explores, and the y-axis is a training loss, you'll see that our self model, or the self-aware model that's driven by curiosity learning, learns to stage its learning of the world in a very interesting way. It first tries to learn ego motion, so it has high training loss at the beginning, and then it gets it, so the training loss decreases, and then it starts to pay attention to object and start to have a hard time learning object, but it gets it, and then it goes to explore more. So that's the rough idea of this work. Of course, this is a really high-level sketch. Another line of work that Kwan and I and my collaborators Yuka, Animesh, and Silvio worked on is actually focusing on interaction with tools. The idea is that tools are really important for humans, especially we are almost the only species that can use tools, and the only species that can do very sophisticated tool building and tool usage. So how do we go from vision to action when it comes to allowing tools, an algorithm to learn to use tools, especially the challenges, the high dimensional visual observation is very complex, and that's what we care about. We want to do this kind of robotic learning in complex visual world. Well, the way we did it is encoder decoder network that transforms the high dimensional visual information into maps it to the action. But there is also a real challenge, is that how do we learn to grasp? You know, it's even if we have this visual transformation, it's hard to know how to grasp and perform the tasks. And a lot of work a lot of people have worked on this. And how do we do this? In this particular particular case, we're demoing that we want the robot not only to grasp the novel object, but also use the object as a tool to perform downstream tasks. And you can see, you can see that it's the same object can be used in different ways depending on the downstream task. And how do we make that inference? So what we did is to rely on a pretty robust and classic idea in computer vision, which is key point representation. And I'm not going to belabor all this previous work, but the idea is if we can infer grasp point, function point, and effect point, 3 important points of each tool, and learn the key point of the downstream task, we can translate this very complex and high dimensional problem from visual input into action space. And here's just an example of, showing how in simulation, the robot is able to infer this complex thing and know how to use the tool in different ways in order to perform the downstream task. Let me just fast forward. Kwang, how much time do I have? Or am I over?
I guess you can, if it would be great if you can finish in 5 minutes.
Oh, I'll definitely finish in 5 minutes. This representation of key point has another really nice feature is we can assemble new tools because we can infer how to use key points to do downstream tasks like pushing, reaching, and hammering. We can infer how to reverse configure a new tool based on the key point to perform tasks, the downstream tasks. And here's an example of this newly assembled tool used for hammering. So, okay, so let me just do the last quick section another thing that's exciting us are these long horizon interactive tasks. And this is mostly work with student Fei-Fei and Silvio. And what is a long horizon task? A lot of you are working on this. So, but I think for me, this is a very exciting area of robotics. And for Fei-Fei, the most exciting long horizon task is making ice latte. And here he wants me to show you 6 times speeded up how he, making ice latte with a professional training is very complex. So I'm not going to finish showing you this whole video, but let's just believe Fei-Fei can make really good ice latte from the initial state to this goal state. But the question is, what do we need to do to achieve this? It's, the initial state and the end state is very different and has many choices along the way. It's very different from navigating a long empty hallway. That's long, but it doesn't require that many different state changes. So one natural way to think about this is to figure out the linear intermediate step. But of course, it's not that simple. In fact, every step of the way, the search space is huge. There are the basic skills we need to figure out. There is the object, especially complex object environment we need to figure out. There is the state of the objects that undergo changes. There's also the overall context and scene and 3D environment we have to deal with. So this is multiplying this together. We have a huge prohibitive search space. So the real challenge here is how do we plan in the combinatorial space of subtasks like object category, state, and scene configuration? How do we learn this and how do we do it in testing time? So the key insight Fei-Fei has is to learn structured task representation. And that's a way to control the explosive space, state space of this learning. And the one work I want to show you, one line of work I want to show you is the one-shot visual imitation, and where the robot needs to imitate and perform a task given one single video. again, there's a lot of people who have done this. I just want to make sure I acknowledge there's a lot of people who have done this and were inspired by many of these work. And so here's an example. Consider this cooking task that has many different subtasks and that we have to consider. And to do it in a sequential way is very difficult, and to try all these states in a sequential way is very expensive. So the insight we have is that we can actually turn this representation of task structure into a hierarchical program, and that reduces task space complexity. So our algorithm, the goal of our algorithm is really just video interpretation and policy execution by neural program induction. And this is an idea that's rooted back to robotics many, many years ago, since the manual task programming days. And but here, what we are trying to do is through this new line of work called neural task programming, by generating neural programs that will act as a reactive policy that controls the robot to perform the demonstrated task. And here's just an example of a learned NTP, neural task program, that's trying to execute a block stacking task. At the top level, we know we're trying to execute block stacking, but the program quickly traverses down to one important move, which is which is to pick and place. And then it goes down one more level to pick and execute this movement of picking. And once it's done, it executes another movement. And once this is done, it knows to traverse back to a higher level and go to the next step. And by doing this, eventually through this hierarchical execution of task, it can perform the goal. Okay, let me just fast forward this. And of course, we have some quantitative evaluation of our NTP algorithm compared to a flat or sequential way of execution. And we show that for unseen tasks, NTP generalizes a lot better. But there is also a problem with NTP. It's actually very expensive, and it needs a lot of supervision. And what we want is to have continuous strong generalization with weaker supervision. So in the interest of time, I'm gonna actually fast forward this. This is the follow-up work we have done since the NTP work called neural task graph inference as an intermediate representation inside the neural network to improve generalization with weaker supervision. It just roughly has two components. One is the task graph generator that takes complex video demos as input and generate the task graph representation. And then the second one is the executor, task graph executor that is essentially is a function as a reactive policy, and the task graph executor decides which action to take based on the generated task graph and the current observation. And we have done this experiment both on a more toy block stacking scenario, as well as AI Thor's simulation environment. And you see on the right that the NTG, the neural task graph, generalizes better than NTP and another baseline. So I know I'm out of time. This is just to remind you that what continues to excite us is this loop between perception and action, and trying to work on these interactive real world tasks. You might be asking, if you paid attention to my title, that I promised babies, kittens, and octopus, and where is the octopus? Well, I want to end with an octopus. An octopus is an incredible animal that has a superb visual system and superb manipulation capability. And this book by Peter Godfrey Smith is one of my favorite books on intelligence and octopus. And I just want to end with this quote, that the original and fundamental function of the nervous system is to link perception with action. And he drew this, as a philosopher, he drew this conclusion through observing literally under the sea the lives of octopus, and has been inspiring me for a long time. So that's the story of the three animals or three intelligent agents I promised you in my title. So thank you very much.